Hello everybody, welcome to the first episode on my series of Projective Geometry. Today we're going to be talking about cross ratios. Now, before we talk about cross ratios, we need to talk about a convention, which is that of a signed ratio. So a signed ratio is something of the form XA over XB. So XA and B are points on a line. And we sign this based off of a convention where X is placed relative to A and B. So let's say you have A and B are points here. So this is A, this is B, and this is a line, so this extends out. If X is here or here, so if X is outside of this segment, then this ratio is defined to be positive. So it's positive out here, and it would be positive out here. But inside, if X were inside the segment AB, then it would be negative. In other words, it's basically saying, XA, you're defining the distance in that direction, but XA here would be defining the distance in that direction. So the order of points matters, and since these are two opposite directions, we basically say that this ends up being a negative ratio. But here, if X was here, XA and XB is in the same direction, and the same applies here. XA and XB are in the same direction, so you get a positive value. Now that we have our convention for ratios like this, we can define the cross ratio. Now the cross ratio applies when we have 4 points, A, B, X, Y. So let's put them here. We have 4 points, and we write the cross ratio like this. AB, and I'll say AB cross XY. Sometimes you can write commas here. It just depends. So AB cross XY, this is defined as XA over XB times YB over YA. So here we see that X and Y are both outside of the segment AB, meaning that both of these ratios are positive. So again, we have different scenarios in which this cross ratio can be positive or negative. In particular, we could have, so here we have the case where AB and XY are disjoint from each other. Then that results in a positive cross ratio. If AB and XY were nested, so let's say we had AB here and XY here, A, X, Y, B. So they're nested. Then this also results in a positive cross ratio because both the ratios XA over XB, we see that's negative, but YB over YA is also negative. And when we multiply two negatives, we get a positive. However, when we have this overlap, so AXBY, this would result in a negative cross ratio. And as it turns out, we'll see in the next video, we really only ever look at cross ratios that are negative, in particular cross ratios that are -1. So that's our definition of cross ratio of 4 points on a line. Well, what if we have 4 lines? Let's say we have 4 lines that all meet at some common point. So we call this point P. And let's say that these are 4 lines A, B, X, Y. So I'm using lowercase to denote the lines. A, B, X, and Y are 4 lines. Well, we can also define a cross ratio that is written A, B, X, Y again. But instead of using these distances, we use sines of angles between X and A, X and B, YB, and YA. So here, this angle here, I'll call that the angle of X and A. And it doesn't matter, since we're taking sines, it doesn't matter whether we do this acute angle or the obtuse angle, right? If we extended, there's 2 different angles that we could define as being the angle between X and A. It doesn't matter because we're taking sines. The sine of both of these angles would be the same. So we define this with similar lettering. So instead of the distance xb, we just take the sine between the lines, the sine of the angle between the lines x and b. And similarly over here. Now we have this plus or minus because we have no convention for, like before we had directed ratios, but here we have no sense of what is a directed sine, right? I mean, sine can be positive or negative, but we're going to have only positive values, right? Because these angles are going to be less than 180 no matter what. The plus or minus essentially comes in as the same order here, right? So if I were to draw a line, and I say these 4 points are A, B, X, and Y, then the order of these points, the sine of their cross ratio gives us the sine of this cross ratio. In particular, the sine is chosen for such a reason that these cross ratios will actually be equal. So if I were to label these points A, B, X, and Y with capitals, then we claim that AB, the cross ratio of the 4 points on a randomly drawn line, right? I just drew any line. I could have drawn a line here or what. It doesn't matter. The cross ratio of the 4 points is in fact equal to the cross ratio of the 4 lines. So let's prove that. The way we do this is with the law of sines. So we have this triangle APX. So I'm going to draw a nice triangle here. Okay. So we have this triangle. So this is P, this is A, this is X. And this angle here is what we're calling the angle between line X and the angle between line A. So this is obviously an important angle. Now, we also have the triangle. It's more right than I wanted it to be, but that's fine. Let's say this is PBX, right? And this is the angle between X and B. Well, we see that in this cross ratio, we have the first part is XA over XB. And in our cross ratio of 4 lines, we have the sine of this angle divided by the sine of this angle, right? And these are related to each other through the law of sines. What I mean is that XB, so the law of sines tells us that XB over sine of this angle, which I'll call the angle from X to B, this is equal to the length of any other side divided by the sine of the angle across from it. But we see that these two triangles share a common side, so it'll be most useful for us to use that side length. So XB over sine of the angle from X to B is equal to PX divided by the sine of the angle. So this angle PBX okay, and I'll write right above it, we have the similar result for XA. XA over the sine of the angle from X to A is equal to PX over the sine of the angle PBA, right? So this is, sorry, PAX, that's what I meant. So we have these two results, and they look pretty much the same. We just replaced A's and B's, took an A, made it a B. We get the same thing. So when we divide, we're going to get pretty similar things. Now, in particular, we see that this angle, PAX, well, there's nothing analogous to this PAX in here, right? So we want it to cancel with something else. And we'll see that it cancels whenever we look at the analogous forms for y. So YA over sine of the angle from Y to A is equal to PY over the sine of angle PAY. So here I'm just, replacing x's with y's. But PAX is this angle here. And that's exactly the same as angle PAY. So these two sines are equal because the angles are equal. So they will cancel out whenever we take this cross ratio. So we have the final result from law of sines. PBY. And again, these two sines are going to be equal to each other. So all we have to do is take XA over XB times YB over YA and plug in all our expressions. So we can solve for XA in this equation. And if we plug in XA, XB, YA, and YB from all of these four equations, so we have four different equations here, and we plug them all into this cross ratio, what we will end up getting is exactly this form. So we take and then the plus or minus is chosen dependent on the positioning of A, B, X, and Y. So it's chosen according to this convention up here. So now we have been able to relate if we have four lines all stemming from one point. We defined the cross ratio of these four lines. And we said that's equal to the cross ratio of the 4 points we get when we draw a transverse line. But it doesn't matter what transverse line we draw. So I could draw this one, and these 4 points, these two sets of 4 points, will have the same cross ratios. So this is one of the crux points of projective geometry. We are now able to project from one line, this line here, L1, to this line here, L2. We project through a point P, right? So we have our line, we have our 4 points, and a point not on that line, and that was bad. And we can project through P to all of these points, and then draw another line, and we have the exact same cross ratio. In other words, the cross ratio is invariant under these projections, and we will see that this is very useful for us in projective geometry. Now, another thing that I'll note here, but I won't prove, is if we have a circle, actually I'll note two things, but here's the first. If we have a circle and we have 4 points on that circle, we call this a cyclic quadrilateral, and we can define the cross ratio of a cyclic quadrilateral much in the same way as we did before. Except we define it in terms of if we take a point P here on the circle and we draw these lines. So we draw these lines and we say that the cross ratio of these 4 points on the circle is equal to the cross ratio of these 4 lines. And what we get is that this cross ratio does not depend on the point P. So the cross ratio is unique to the 4 points, A, B, X, and Y. And since we've said that it's equal to the cross ratio of the 4 lines, then we can project from a circle onto a line. Similarly, if we have a circle, or here, let me use the shape tool. If we have a circle and we have some cyclic quadrilateral here, let me try and, this is a pretty hard picture to draw. I tried. And if we have a point P that's not on the circle, but we draw, let's say, these lines from P to our points. I don't know why the shape tool isn't making these lines, but I tried. And we get 4 new points where the lines intersect the circle again. Then these two different cyclic quadrilaterals will have the same cross ratio. So these are 2 important results, but I won't prove them because they're pretty much the same as this proof here, just using law of sines. So that was the video on cross ratios. I hope to see you in the next video.